Hi, everybody. Welcome to Math 70. Today's lecture is section 2.1, Introduction to Linear Modeling. So linear means we have a linear function, which we often write in slope-intercept form, y equals mx plus b. And modeling means we use the function for applications from the real world or the physical world, um, things like that. So we're not just working with the pure abstract mathematics, we're going to be using it to work with questions about the world. So I want to remind you of our four representations of mathematical ideas. And the fact that we can connect and convert to each of them. And that doing that can help us answer questions about mathematical situations, for example, linear modeling. So in a lot of linear modeling, we start with the verbal. We start with an explanation about a situation. And in order to understand it mathematically, we frequently end up in the symbol representation. But there are also times when we're given information about numbers or given information about graphs that can help us. And even when we're not given these, it's a good idea to switch to these to help us get to the symbol representation. So I'm just jump right in with an example. Let's see, Joe has a savings account with, let's say $53 every week. Joe adds $72 to the account. So this is our situation. This is a verbal representation, and we can convert that to a symbolic, a visual, or a numbers representation. And then we can ask questions based on the situation. Before I ask the questions, I'm just going to switch it to each of those other representations. So a lot of times when you're given a linear equation or linear modeling question, the numbers representation is the easiest. So let's let X be the weeks, and let's let Y be the dollars in the account. So if Joe starts a savings account with $53, that means in week 0, Joe has $53. And every week, Joe adds 72. So when we move up 1 week, we're going to add $72. And this is the key to make it a linear modeling, is it changes by addition or changes by subtraction. That's $125 there. After another week, we're going to add another 72, which is 197. Often you won't see the plus part, you'll just see the table. But I like writing the plus to remind myself what's changing on the input and what's changing on the output. Let's do a couple more. Next week, we're going to add another 72. That's 269. I'm doing this in my head. I could be making mistakes. You're welcome to use a calculator or to do the addition a little more carefully. And we'll go one more week. So add 72 one more time. That would be 341, I think. So now we have a numerical representation of Joe's bank account. From this, I could turn it into a graph, and to do that, I'm actually going to switch us over to desmos.com to show you how easy it is to build a graph. And actually what I'm going to do is I'm going to build a table in Desmos, and from there we're going to build the graph. So if you use this plus sign, you can add a table, and then let's add our first 4 weeks and our money. Kind of hard to see, I will admit, because of the scale. So this gives me a chance to show you something else you can do with Desmos. If you come up here to this wrench, you can change your x-axis. Well, our smallest x was 0. I'll put in -2 just so we can actually see. Our biggest x was 4, so I'll put in 10. That's probably enough. And now notice the x-axis increases by 1 and the y-axis increases by 100, and that allows us to see that, yes, this is a linear relationship. All these dots fall along a straight line representing the money. So this is a visual representation. And if we want to think about connecting those dots in a line, we need the formula. So the formula here says, and I'm going to write it here, I'll write it on the notes later, y equals, well, what did we start with? We started with $53. And each week we added 72, so 72x. This maybe is how you would build it first. This isn't quite mx plus b form though, because it's backwards. So I'm going to write it as the slope 72 times x plus the initial value 53. And here we have our symbolic form, and we can see that it looks like I did it correctly, more or less, because all those numbers are falling, or all those dots are right on the line. And now we can ask questions using the graph, using the table, or using the formula. So let's actually ask the question, how much money will Joe have in week 10? If we want to use a table form, what I would recommend we do is we just work our way up. 341. Let's see if it works if I just add 72. It does, but it doesn't tell us what the number is, so that's not so helpful. But we can do some work down here. 341 plus 72 is 413. Plus 72 is 485, and so on and so forth. Let's do 485 plus 72. 557. 557 plus 72. 629. 629 plus 72. 701. And I can do this last one in my head, 773. So this tells me that after 10 months, or sorry, 10 weeks, Joe has $773. And this is using the table representation, and that's a totally valid way to answer that question. You can just add your way up step by step. I could also use the formula. I want 72 times 10 plus 53, and there it is, there's the 773. This is a reason we often convert from words to symbols, because then the arithmetic becomes very fast. It took me a while to get from 4 weeks to 10 weeks in the table. It did not take me very long to use the formula. And I could also, let's say if I didn't have this one here, I could also use a graph and just get as close as I can to 10. There it is, 10, 773. So when the x is 10, the y is 773. All right, I know that none of this is going to be in your notes, so I'm going to transfer it over real quick to the notepad. This one's going to be a sketch of the graph because I can't do it that precisely. Here's X, here's Y. That point right there is 53. And every time I go up by 1, I'm going up, so the slope is 72. And then the symbols are y equals 72 times x. If we're adding 72 each time, that means the slope is 72. That's how you build your formula from your table. You look at the change in y divided by the change in x. 72 divided by 1 is 72. And then to find the starting value, or the y-intercept, you look where x is 0, and there's your 53. And so now I can ask, how much does Joe have in week 10? And so we could add 72 each time, and eventually we get down to 10 and 1073. Or we could look at our graph and go out until we get to the point 10 here, and that's 773 there. And the way we will often do it, it's not the best way, it's not the most flexible way, but it's the fastest way, is we build the symbolic formula. So we have that. And so now we put 72 times 10 plus 53, which is 720 plus 53, which is 773. We can also ask questions like, when will Joe have, let's see, at least $400? It's unlikely that we're going to land exactly on 400, which is why I put the at least 400. And we can also solve this using a table or our graph or our formula. If we use our table, we're just going to keep adding until we get to the 400 at least, and there we are. When the week number is 5, Joe has 413, so at week 5, Joe has at least $400. In fact, Joe has exactly $413. Or we could use our graph. And if we want to use our graph, what we would do is we'd say, okay, here's 400. What's the x value for 400? And it turns out to be something very close to 5. And I'll show you this on Desmos as well. And that tells us that when we're at $400, our week is at 5. And I know the scale on this graph is terrible. And finally, I can use the symbolic formula because I want to know when Joe has 400, at least $400. So I'm looking for the week. So I set up an equation where I now have to find out what x is. And here's our multi-step linear equation. And we solve this like we did in chapter 1. Subtract 53 from both sides. I have 347 equals 72x. Divide both sides by 72. Maybe we grab our calculator and that we find x equals, I'm going to do the math real quick on another screen, 4.82, which is approximately 5 weeks. All right, this page contains a ton of information. It contains all 4 representations of the mathematical idea. We have the verbal one that we started with. We built ourselves a numerical representation and a graphical representation. And we built ourselves a symbolic representation as well. Let me write graph and symbolic. You may be comfortable going directly from the verbal to the symbolic. That's fine. And then you could use the symbolic to make your table. Or maybe you do what we did and you start by converting the verbal into the numbers, because that's, for me, that's a little bit easier. Because if I know he starts with 53, then I can do 0, 53, and every week, add a week, add 72. And once I have this numeric representation, then I see the change in y over the change in x gives me the slope, and the initial amount gives me the y-intercept. All right, let's do one more, and then that will wrap up the video for this section. All right. Anne is 200 miles from home. Every hour, and let me phrase it differently. Anne drives towards home at a constant speed of 35 miles per hour. Not very fast, but it will work. So I could ask questions like, how far away from home is Anne after 2 hours? Or how long does it take until Anne is 100 miles from home? Or when does Anne reach home? So we can ask a lot of questions about this mathematical situation. And to answer all those questions, I recommend that we build ourselves our 3 other representations. So let's build our numbers representation first. X is time in hours, and Y is distance in miles. So at the beginning, Anne is 200 miles from home. And if it's a constant speed, then every hour that goes by, we're going to get 35 miles closer to home. So that means the distance is going down. So this is going to be a linear equation that goes down over time instead of going up. And as we keep adding hours, we keep taking away distance. Let's see, 95 and 60 and 25. And notice if I try to go to 6 here, this would be negative 10, which doesn't make sense. Because you can't be negative distance from home. So our model, and this brings up an important point, all models, as soon as you take a mathematical model and you apply it to the real world, there's going to be a point at which the model doesn't make sense anymore, because our real world has constraints, it has restrictions that a pure mathematical model won't have. Nevertheless, this is a good way to get an initial idea. And so now let me convert this to a graphical. So at time 0, or 200 miles, and driving at a constant rate, that's a really nice way to see how that's definitely a line. Right? Because we could do it by 1 hour, but we could also do it by half an hour or even minute by minute if we wanted to. And our graphical model has a decrease where the slope is the change in y over the change in x, minus 35 over 1, the slope is minus 35, and the y-intercept is 20. And now that I pull that information out, it becomes easier for me to do the symbolic form. Y is minus 35x, because minus 35 is the slope, plus 200. And now I can answer all sorts of questions. How far away is Anne after 2 hours? Well, if you ask me that, I'm going to go to the numerical representation. I see it right there, 130 miles. Easy. What about how far away after 2.5 hours? Well, my table doesn't have it anymore. And when you sketch a graph, it's hard to be precise. So I'll use my symbolic form. I'll do minus 35 times 2.5 plus 200. Minus 35 times 2.5 is, let's see, 70, and 17.5 is minus 87.5, I think, plus 200. So that's 112.5 miles. All right, so the symbolic form is really useful for that. And when does Anne reach home? Well, I know it's going to be less than 6 hours, but because the table shows me that by the time I get to 6 hours, the output seems to be negative, which doesn't make sense. So it should be less than 6 hours. And if I use Desmos to graph this function, I would see that this point right here is somewhere between the 5 and the 6. And so probably the way I would answer this, if I went ahead and graphed it in Desmos, so let's do that, is I would probably just go ahead and use Desmos to graph it. Hold on one sec while I pull that up. So here's Desmos. Let's clear these other pieces. I won't remake the table here. I don't want to take that time, but I can do y equals minus 35x plus 200. And Desmos is nice enough to give you important intersections. And so I can see when time equals 5.71429, et cetera, et cetera, et cetera, distance is 0. So that's my answer, 5.7 hours approximately. 5.7 hours from Desmos. That's an excellent way to answer that question. If you don't have Desmos, you can also get, an estimate from your table. You can say a little less than 6 hours. That's a good answer. Or we could use our symbolic form. And we can say if distance is 0, that means y is 0. And I'm trying to solve this multi-step linear equation. Subtract 200 from both sides to isolate the x, and I have negative 200 equals minus 35x. Divide both sides by minus 35, and I get 5.71 dot 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 equals x. So about 5.7 hours. All right, one more example, because I want to show you how sometimes your table doesn't give you x's that go up by 1, but you can still find the slope. So here's my example. Make sure I know what I'm sharing here. Okay. Let's see. Kim is bedazzling a hat. Bedazzles, she's putting beads on it. Kim's putting beads on the hat. There are already 14 beads. Every 3 minutes, Kim adds 5 beads. I don't know if that's a good rate of adding beads. I've never bedazzled a hat. but it'll work for our example. So let's practice going straight to the symbolic from the information, although it's always okay to work through the numerical. So for the symbolic, let's start by writing down what the function looks like in its general form. This is a linear model. So we're going to use y equals mx plus b. M is the slope. B is the y-intercept. This is step one when you go from words to symbols, is identify the model and its formula, name the important pieces of the model. X here is the minutes, and Y is the beads. It's also a good idea to remind yourself, since there's a lot of letters floating around, that X is a variable and so is Y, because these change, and the slope and the y-intercept, these are numbers, these are not going to change. So if m is the slope, it's the change in y divided by the change in x. So it's the change in the number of beads, 5 beads, divided by the change in the minutes, 3 minutes. The slope is 5 beads every 3 minutes. And we can take that, I'm sorry, I blocked it. The slope is the change in y, it's the change in the number of beads, divided by the change in x, the change in minutes. So you can pull that information directly from your sentence. And the y-intercept is your initial amount, which here is 14. There are already 14 beads. And once we have our information and our formula, we can go back and we can plug it in. Since y is a variable, it stays as y. Our slope is 5/3. X is a variable, it stays as x. And our y-intercept is 14. Let's build a table. X and y. X is minutes, y is beads. At time 0, we have 14. We don't have a time 1. We jump all the way up to a time 3, so we're adding 3 here. And then we add 5 here, and we get 19 beads. So in this case, every time we go down the table, we are adding 3 minutes, because that's what the sentence, that's what the verbal representation told us. One more, plus 3, 9, plus 5, 29. Okay. Nevertheless, we can still find the slope, because the slope is the change in the y divided by the change in the x. The slope is still 5. We've gone up 5 in the y every time we go up 3 in the x. So you can still pull the slope out very easily from the table. You just have to remember it's the change in y divided by the change in x. In our earlier examples, the change in x was 1 every time, and so it made it really easy to find the slope. But even when the change in x is not 1, we can still find the slope. And then the y-intercept, we still read off when x is 0, y is 14. And now we can answer all sorts of questions, like how long will it take until Kim has at least 50 beads on the hat? When will Kim have 60 beads on the hat? And at what point will Kim stop putting beads on the hat? Right? There's going to be a maximum number of beads. Maybe it's 100, maybe it's 200. But after that, our model's not going to work anymore. And we could draw a graph if we wanted. I'm not going to draw a graph here, just because I've done a couple by hand. But we can just put that formula right into Desmos, and it'll give us the graph. That's our video. Thanks for watching. Next video coming up soon.